All right, so we're going to be taking notes on probability distributions, which is something that we started a little bit last time, but we'll just kind of formalize it a little more in notes. So first, just a few vocabulary words that will help us describe the type of probability distributions we're doing. So the first one is going to be discrete data. So that is specifically or generally like whole number data. So things like Wordle scores, that is an example, because your Wordle score that we saw last time, that can be 1, 2, 3, 4, 5, or 6. It can't be 2.2, it can't be 3.8. It has to be one of those things. It's not always just whole numbers. It could be things like shoe sizes, which often shoe sizes are like size 8.5, 9.5. That's fine too. It's still not continuous data because it is a number, but also kind of like a category. You can just be 6.5. You can't be 6.6. You can't be 6.8 for a shoe size. So discrete data, that's a specific value. So if we were looking at it visually, it would be a bar graph rather than a histogram, because our data can only be at these specific values. It can't be at the ones in between. Continuous, that's the other way. So that would be when data can be any value. So things like height or time are good examples. AGI, height or time, since you can have decimals up to any amount. So instead of it being a bar chart, we could have a histogram where the values are touching, because you can be any time. It doesn't just have to be 3 seconds or 4 seconds. It could be 3.6, 3, 2, 1, 4 seconds. It can be any value. So continuous data is that. We're going to be dealing with discrete data today because we're doing what's called discrete probability distributions. So that's when our possible outcomes are numbers, specific numbers, not ranges of numbers, but specific numbers. So the notation we'll see is this, and the way we kind of translate that notation into more language that we're used to would be, so this one right here is probability that event, and that's a big X, so big X has outcome little x. So those are our outcomes. So for some examples, so with dice, this example A here is let big X represent the value of a single dice roll. So our event is big X, our event is rolling a dice, and we want to know what are the odds we're going to get these outcomes here, this 1, 2, 3, 4, those are our little x's, those are our possible outcomes. So for this first one, what are the odds that we roll a 1 when we roll a dice? So dice have 6 sides, so the odds we're going to roll 1, we should expect to get that 1/6 of the time. We'll just keep it as a fraction here. And that's going to be same no matter what the outcome is. What's the probability we're going to get a 2? It's still 1/6 all around for a dice. The probability that we get each of those outcomes are 1/6. So here when it says find P of X equals 5 and describe the meaning and context, so to translate that one, it would be the probability that our dice roll outcome is 5. So the probability that our dice roll outcome is 5 is 1/6. So we should expect that 1/6 of the time we roll a 5. All right. To get ourselves a slightly more complicated example here, so we have let big X represent the value of the sum of two dice. So now our event is that we're rolling two dice and taking the sum, and our different outcomes are the possible sums. I included our sample space diagram for this one, so a reminder that like these are saying if we roll a 1 and a 1, our sum is 2. If we roll a 3 and a 4, our sum is 7. So those are all of our possible outcomes. So we know that there's 6 times 6 or 36 different possible arrangements of the two dice, and there's only one of them that gets us a 2. So the probability of our sum being 2 is 1/36. A 3, there's 2 ways to get a 36, to get a 2, to get a 3. So 2 out of 36. There's 3 ways to get a 4, so 3 out of 36. And then we can just keep filling out the table from there. So there's 4, 5. So there's for 7, we see there's these 1, 2, 3, 4, 5, 6. But then after that, it starts going back down again. So we'll bring it back. All right, it's a little tricky to do this without you all because I often make mistakes, as y'all know, and I have to catch myself today, but I think I'm all good here. Okay, so here, find the probability of big X equaling 5. What that means in context is the probability that our event X, so the sum of our dice is 5. So probability that the sum of the dice is 5 that is us right here. So 4 out of 36. That would be the same as 1/9 if we simplified that. Okay. All right, so those are probability distributions as a table. On this next page here, we're going to look at them on a graph. These tables are just copied for us so we can see them near our graphs. So it tells us probabilities can be modeled using functions, which means they can have multiple representations, such as a table, graph, and equation. So we already saw table. We're going to look at a graph here. So our part A, so our dice roll, our options were 1, 2, 3, 4, 5, and 6. And our axis here is our probability. So let's see, probability. And for option A, our table is always saying 1/6. So we really only need one number on our y-axis, which is 1/6, and then all of our dice roll outcomes are at that same probability, so at that same y value. We have a special name for distributions that are like this, where we expect every single value to be equal. We call this a uniform distribution. So uniform distribution. We'll see a lot more of that in some of our next lessons too. Probability B is going to be a little bit more complicated because we have a lot more outcomes and the probabilities of those outcomes are not all the same. So down here, our dice roll, and really it's the sum of our two dice. And then this will be our probability. And this one, we broke it up out of 36th, so we can be anywhere from 1/36, 2, 3, 4, 5, up to 6/36. I'll label this one too as 5/36, but we don't need to label each one. And then we'll have our sums, so 2, 3, 4, all the way to 12. All right. So the odds, we get a 2, that's 136. So I'll just make my little bar, and it's going up kind of 1 by 1 until we get to 7, and then it's going to go back down. Okay. All right. Seeing it as a visual helps us see the pattern a little more of that symmetry within this, and then also that 7 is our most likely outcome at 6/36 or 1/6. Yes, okay. So moving on to this next one. So expected value. So find the expected value. We have this formula. It looks a lot scarier than it actually is. For example, if you look at even just the formula for mean in your formula Padlet, it's going to look really complicated like this, but really it's not too bad. This symbol here kind of making things seem more complicated than it is. What that symbol means, this one here, that just means the sum of, so add up. So when we see this symbol here, it means add up. And what we're adding up is the probability of x, so our outcome, little x, times the probability of that outcome. So that is outcome, little x, times, and then this part here is saying the probability of that outcome. So probability of that outcome. So this is really connected to the mean. It's like we're finding the mean, but for just one person, or just one event happening. So find the expected value when rolling one dice. So we need to add up the outcomes times the probability of that outcome. So the first outcome is 1, and we're looking up here for this. So our first outcome is 1. The probability of that outcome is 1/6. So we'll multiply it. We will keep doing that. So add up the next outcome, 2 times the probability of it. So 1/6 plus 3 times 1/6 plus 4 times 1/6 plus 5 times 1/6 and plus 6 times 1/6. All right, so we're gonna need a calculator for that. As I get my calculator from my backpack, you all should do that too. Okay. I dropped it. We're good. Okay. Here we go. So 1 times the 6th. So I'm just typing it all in. Okay. All right. So I am getting 3.5 when I do that, which if we think through, that makes sense because it's like we should expect to roll a 1, 2, 3, 4, 5, and 6 all one time. And then we divide by 6. So we'd get the same thing if we just did 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. And yep, still 3.5. Okay, so expected value for that one. Our next one has a little more going on. But it's still the same idea. We think, okay, what's our outcome? And then what's our probability of that outcome? So now we're looking up here. And so our first outcome is a 2, and then there's a 1/36 odds of that happening, and then we keep it going. So 3 times 2 over 36 plus 4 times 3, 36. And then we just keep going for each of these, multiplying the outcome and then the probability. Outcome, probability, outcome, probability. So we got to finish this one out. Alright, I'm going to continue down here. Oops, well, let's see. 9 times 4, 36. 10 times 3, 36. 11 times 2, 36. And 12 times 1, 36. A note here, when we type this in our calculator, this will be the same so to avoid having to type in over 36 over and over and over again, we can do 2 times 1 plus 3 times 2 plus 4 times 3. So I'm just borrowing from all of these. So 2 times 1, 3 times 2, 4 times 3, 5 times 4. We can just add up all of these and then divide by 36 once. It's not wrong to do it just the way as we've written it out, but since all of the denominators here are 36, we can combine them into one big fraction. It's like how we can add up 1 quarter plus 2 quarters into 3 quarters. Okay, so typing it in. So 2 times 1 plus 3 times 2 plus 4 times 3 plus 5 times 4 plus 6 times 5 plus 7 times 6 plus 8 times 5 plus 9 times 4 plus 10 times 3 plus 11 times 2 plus 12 times 1 equals that divided by 36. Okay, I'm getting 7, which makes a lot of sense. Oh, that was odd. Okay. Yes, 7, which is what we already can see from looking here. It will not always be that the tallest bar is your expected value. It will be true if the data is perfectly symmetrical like ours is. But even when we think about our uniform distribution, our expected value was a 3.5. So it wasn't even one of our bars, and that's okay. But for symmetrical data, you will find that the expected value is if it's symmetrical and the highest bar is in the middle, that will be your expected value. All right, moving on. So let's see. All right, here we go. Okay, so discrete probability distribution functions. So this is one where we make an equation to represent the probabilities, since for probability distribution functions, our inputs or our outcomes are always going to be numbers. So for this one here, we've got a function where our input t is going to be a possible outcome, and then our output, p of t, is the probability of that outcome. So let's see, we'll label, so our input is outcome t, and then our output is the probability of outcome t. And so something that's going to be true for our probability distribution functions is each probability has to be between 0 and 1. Otherwise, it can't be a probability. And then another thing is all of the probabilities must add up to 1. Yeah. Sorry about that. Okay, so let's see. We can use this criteria to test if a function is a probability distribution function. And so we'll do that on the next page a little bit. But first, we're going to do some writing of probability distribution functions. The first one will be pretty easy. The second one will be a little harder. So if we're back to our example A that we've been following along with, so let x represent the value of a single dice roll. No matter what our input here is, as long as the input is a number on the dice roll, or a number on the dice, then it's a possible probability. So when we're here, we can say our probability distribution function, so f of t equals 1/6. It's always going to be 1/6. It doesn't matter what our input is, our output is going to be 1/6. What we do need to do though is we need to specify what our possible inputs are. There's a few ways we can do this. Usually we'll see it in brackets. You can see where t is within. You can say 1, 2, 3, 4, 5, 6. You could have also said it as for t values that are greater than equal to 1 or less than or equal to 6, as long as t is an integer. So that's how you say it's only the whole numbers between 1 and 6. When it's not too many numbers, I usually just write it out since it's not too hard. But if there's lots and lots of possible inputs, it is nice to shorten it to just having to write the boundaries and then specifying what type of number you're looking at. Okay, for part B here, so looking at this, there is definitely a pattern we see. We saw it in our graph where it kind of went up and then down. But one thing we know for sure is going to be in our function. So if I call it f of t for this one, we know that no matter what, all of these have a denominator of 36. So we know in our function too, okay, no matter what, we're going to have a 36 down here. But to get our probabilities, we need to then now connect, okay, how does 2 connect to 1? How does 3 connect to 2? 4 connect to 3, 5 connect to 4. How does our input, our roll, connect to our probability? And from the first two numbers, there seems to be a pretty good pattern. We just need to take the roll, subtract 1, and then divide by 36. 2 minus 1 is 1. 3 minus 1 is 2. 4 minus 1 is 3. So if we start there, okay, if we say our f of t will be our little t, our outcome, minus 1 divided by 36, that is pretty good. That works for most of the values, but it stops working once we get to 8, because at 8, if we were to keep the pattern going, if we did 8 minus 1, we would get 7, but we want to get 5. So it stops working. And so if we're trying to, one thing we can do is we can specify that our function, like this part of the function, this works for our t values from 2 to 7. So we can say from 2 to 7, and our integers between 2 to 7, this function works, but we'll need a separate function for the rest of the numbers. So to do that, what can help us to see is we can think about how there's some symmetry on both sides here. So when when we think of symmetry, a function that'll help us a lot that we haven't really used much in this class or probably your previous classes, but the absolute value function. So taking the absolute value of a function, that's like how 3 and -3, when we take the absolute value, it's just 3. The absolute value is kind of like what's the distance between this number and 0, which is close to what we want. We care about numbers that are the same distance away from 7, like 6 and 8 are both the same distance away from 7. So something we can do to treat the number 8 just like the number 6 is we can say, okay, any number that's the same distance away from 7, we can treat the same way. So if we say the absolute value, or if we take our input, we're using our input t. So if we take our number t and subtract 7, this function right here will treat the values the same distance away from 7 as the same. So for an example, if we do 8 and 6, if we do the absolute value of 8 minus 7, we get 1. If we do the absolute value of 6 minus 7, 6 minus 7 is -1. The absolute value of that is -1. So this is a part of that function, but there's an issue because we don't just want to say that treat 8 and 6 like the same. We want to say treat both 8 and 6 like the number 6. So what we can do there is our function would become, so f of t equals, if we take 7 and then subtract the absolute value of t minus 7, and then subtract 1, it's a lot going on, and divide it by 36, it ends up working for us. So to look at an example here, if we look at, so we're here, if we look at 8 again, if we did, so I'm going to go over here. If we do 7 minus absolute value of 8 minus 7 minus 1 over 36, we would get 7, and then 8 minus 7 is just 1, so 7 minus 1 minus 1 over 36, I'd get 7, 6, 5. I get 5 over 36, which is what we got in here. The same would work if instead of doing 6, instead of doing 8, I did 6, because I should want them to have the same value. Then I would still have the same thing, because 6 minus 7 is -1, but then we take the absolute value, it becomes positive. So it's still 7 minus 1 over 36, it's still this. This is a pretty complicated example. It's not often that you have to write ones that are this complicated, but so don't worry if you're feeling a little confused on where did that whole equation here come from. If you're able to see that, yes, this whole equation works, then you're good to go. So we actually no longer need to split it up in two. We can say this function here, this will always work. It works for the ones both before 7 and the ones after 7. So this function works for t values from 2 all the way to 12 as long as t is an integer. So again, if you're feeling a little confused on how we built that equation, don't worry too much about there. If it makes sense why, let's get this out. Okay. If it makes sense why this one here works for the first half, you're in a good spot. And if it makes sense why this one works for all of them, that's like a bonus for now. Since this is more complicated, part B is more complicated than most of the ones you'll end up seeing. Okay. So the most common way that you will be using probability distribution functions is you're going to show whether or not something is a probability distribution function. And to do that, you'll use a table. So for this one here, we've got, what do we have? We've got our function t. All right, you are now getting the family group chat of it being my mom's birthday, so hopefully that does not keep going too much. All right, t and f of t. So our possible outcomes are t's within the integers. It really should be one of the fancy z's. 3 to 7. So our possible outcomes are 3, 4, 5, 6, and 7. So the way we get our probabilities is we input our different outcomes. So t minus 2 over 15. So 3 minus 2 over 15. We'll have 4 minus 2 over 15. 5 minus 2 over 15. Yep, 6 minus 2 over 15. And 7 minus 2 over 15. All right. So now what we need to do is we need to verify, if we look back, what does it take to be a probability distribution? Well, we've got that each probability must be between 0 and 1, and the probabilities have to add up to 1. If the probabilities add up to 1, that first one is going to be true, unless there's negatives, which wouldn't make sense because we can't have negative probabilities either. But let's just simplify these a little and show that they add up to 1. So 1/15, and then we'll have 1/15, we'll have 2/15, 3/15, 4/15, and 5/15, and then we've got 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, whoa, wait. Do they add up? Okay, 1 plus 2 is 3, plus 3 is 6, 7, 8, 9, 10, 15. Okay, yeah, we're good. So equals 15 over 15 equals 1. So we can say all probabilities are between 0 and 1. And they all add up to 1. So that's what it takes to show something is a probability distribution. Okay, let's see. Another thing you'll often do is you'll find variables that will end up making something a probability distribution function, and you're going to be using this same idea that all the probabilities need to be between 0 and 1, and most specifically that they all add up to 1. So we're told here that this function f of x equals x over 19, where x is 1, 5, 7, and k, is a probability distribution function. So we need to find the values of k. So we're told here we've got x and f of x. Our inputs are 1, 5, 7, and k. And we need to show that it's a probability distribution function. So our outputs here would be 1 out of 19. We'd have 5 out of 19. We'd have 7 out of 19. And we'd have k out of 19. In order for this to be a probability distribution function, these all need to add up to 1. So we're going to have 1 over 19 plus 5 over 19 plus 7 over 19 plus k over 19 has to equal 1. I'm going to write it as 19 over 19 just because that will help me more directly see what k is. So we've got 1 plus 5 plus 7 plus k have to equal 19. 1 plus 5 plus 7. So that means 6 is going to have to equal k. That's how we get it all equaling to 1. All right, so another format you might see this question in is instead of k, your variable being in the set, so being one of your possible inputs and might be a part of the function. So here we're told our probability distribution function for our values b are 0, 1, 2, and 3. And then our function is 4 minus b. So it's going to, or k times 4 minus b. So here it's going to be k times 4 minus 0, or just 4. K times 4, or 4k. Here it's going to be k times 4 minus 1, or 3k. Here we'll have k times 4 minus 2, or 2k, and then k times 4 minus 3, or what is that? Just k. So we know that all of these 4k plus 3k plus 2k plus 1k have to add up to 1. So that's 4, 5, 6, 7, 8, 9, 10 k's equaling 1. So that means k has to be 1/10 in order for that all to be true. So again, both of those are using the fact that they all have to add up to 1. All right, that is all for our notes. I know that was kind of a long one, but I hope it's mostly making sense and you all are feeling ready to do homework. So you all are good to do that for the rest of today. Both of them are out. This first one is the one due next block period, and this one is due next week. But you all have what you need at this point to do all of them. So yeah, all right, that is all. See you all next week.